Welcome to another unit in business mathematics. This time I'm going to talk about how we can determine extrema, meaning maxima, minima, for functions with one variable. Actually, it's pretty straightforward. We have the so-called necessary and the sufficient condition. The necessary condition simply means that we get potential extrema. So basically, every x that fulfills this condition could be maximum, could be minimum, but not necessarily has to be one. Well, what does the necessary condition actually signify? Well, it's relatively easy. It means first derivative is zero. First derivative is zero means that at this point, the slope becomes zero, so the function flattens out. If I grow, then the curve flattens out, then I decrease again, that's obviously a maximum. If the other thing happens, I'm going downwards, flatten out, going upwards again, I have a minimum. But that's only two of four possibilities. I can be going up, then after I flatten out, I can go up again. Same thing with downwards. That's actually called saddle points. Saddle points are no extrema. Therefore, if I have a saddle point, it will also report a first derivative of zero, but still not an extremum. So I need to check additionally whether I really have a maximum or a minimum. That's where the sufficient condition comes into play. And here we actually have quite a few of different possibilities to go about this. The easiest way, get the second derivative, insert the potential extremum from the necessary condition, and check whether the result is negative or positive. If it's strictly negative, it's a maximum. If it's strictly positive, it's a minimum. If it's zero, we actually cannot say anything about this, so we don't know whether this is maximum, minimum, or saddle point. So not necessarily does a second derivative equal to zero signify a saddle point. Could also be a maximum or minimum. However, we still have an alternative to go with. The easiest one is we take the first derivative and actually do what I described earlier. So we take a value slightly to the left and another one slightly to the right of our potential extremum, and we check what is their slope. So basically, what is the slope slightly to the left and slightly to the right of the potential extremum. Whenever we have a sign change, so if before it was positive, afterwards it's negative, or the other way around, we know we have an extremum. If there is no sign change, so if it stays the same, we actually have a saddle point. In particular, as I said before, if we have a minus plus change, so we're going down, then we're going up again, this means we have a minimum. If we have a plus minus change, so we're going up, and then we're going down, then we have a minimum. And as I said, well, the alternative is we do not have any sign change at all. Then we have a saddle point. So for the saddle point, a second derivative is zero and we get no sign change. However, well, you don't need the condition for the second derivative. So if you just want to save time, you can directly go and consider only the version with the first derivative. However, here it's important that if I said go a bit to the left, a bit to the right, you cannot overlap any other potential extremum, any other potential pole. So you can really only move a very small part to the left and to the right. And a final comment. Well, The necessary condition gives you a potential extrema. However, you could get a potential extremum which is an invalid solution. What does this mean? Well, it could be that you get a solution which, if you were to insert this in the original function, might actually pose a problem because it's not in the domain of the original function. In this case, this is not a real extremum. It's just, well, again, a potential one. It's an invalid one. So you can directly erase those invalid extrema as well. This happens, for example, or could happen if you have fractions, if you have square roots, if you have logarithms. And well, that's already everything I can mention here in this context. So I hope you enjoyed this short session, and I say goodbye and see you next time.